about coherent optics, how they work, scary physics, but pretty pictures. Is that a good description?
Perfect. Thank you, Fergus. Yeah, my name is Thomas Weible, co-founder and CTO at Flex Optics, and I really like this lineup now. Actually, it's not a talk now, and together with Matthias and Byron, we didn't know that we are in this lineup. It's like a DWDM workshop for you guys now, in a nutshell. Thank you. So this perfectly fits as well now about coherent optical transceivers. Byron and Matthias mentioned it already. So this talk is mainly split into two sections. It's a little bit about theory, no worries. Maybe there is an exam, no, there is not an exam at the end. And then some practical experience, especially for Nokia. Where are you? We did some practical workshop with Nokia together and integrated coherent transceivers in the Nokia gear and showed the output, how Nokia implemented it. So where are we coming from? 10 years ago, roughly, let's say, DWDM has been around for a long, long time, but the challenge there was big cards, big transponder cards, and to get out the light of the transponder card. What is so special on those transponder cards? There is a chip called DSP, the digital signal processor, which actually enables coherent DWDM technology. Now, moving towards 400 gig, the biggest challenge was there to make it really small, especially the digital signal processor, to produce it in a small, nice way that we can squeeze it into a form factor like a QSF PDD. And today we are able to do 7 or even 5 nanometer chip productions. And for sure, the smaller the grids inside of the chip, the smaller the entire housing gets. So the DSP is now inside of the coherent module, and that's actually the game changer. So a coherent module, or let's say the coherent technology, for me personally, it's really a game changing in industry, and I will show why later on. So let's first of all start with where we are coming from. Direct detection, that's, let's say, typical on-off keying method. We have what you see here on the upper left diagram. It's a typical rectangle shape of 1 and 0 signal at the end of the day, or state, and representing one symbol. And on the lower one, actually, that's basically how it looks like when it hits the receiver. So it's not a rectangle, perfectly shaped signal any longer. It's going to be more a sinus wave form, or even some other artificial thing. Now, if we would use the techniques which we have done so far, just increase the frequency, the diagrams would change slightly. So the rectangle shape is just getting narrower and narrow, and the sinus form is getting narrower as well. But also the light levels or the power levels are getting way harder to distinguish between a 0 and a 1. And if we increase it even more, you can imagine for the receiver on the lower one, it's getting really hard to detect what is a 1 and a 0. I think it's even hard for you guys to detect where is the 1 and where is the 0.5 on the screen. So beside higher frequencies for light, light has way more properties, and that's what I want to talk now about. So beside the amplitude, we also have phase and polarization. And let's start with the polarization. Quite a lot of you here in the audience use privacy screen on your laptop, and actually that's a polarization filter. Or if you wear sunglasses, they also filter certain polarization directions. For coherent pluggable, we make use of 2 polarization directions. Typically, it's going to be used the Y plane and the X plane. And with these 2 polarization planes, we can encode actually double the amount of data. So how does this look like? I do have here now a 16 QAM modulated. To the 16 QAM, I come later on the Y plane. And on this, the same signal on the X plane looks a little bit different. It looks like this. And now when you combine those 2 planes together, and we are living in a 3-dimensional world, your actual signal looks like this. This artificial sculpture that's going to hit the receiver, and the receiver is going to differentiate there between the two polarization directions and also calculates the zero and ones out of the signal. So beside the polarization, I already mentioned it, it's the 16 QAM. And what is the 16 QAM stands for? So QAM is quadrature amplitude modulation. It's a modulation scheme, and we make use of complex numbers. So what you see here is a 4x4 matrix with 16 dots, and on the x-axis, it's the in-phase component, the real part. In comparison, have a look at PAM4 modulated signals or the NRZ, which is the green square or the blue star there. There is only the in-phase component. So with NRZ we have 2 states or 1 bit per symbol. With PAM4 we have 4 states or 2 bit per symbol. And with 16 QAM, at the end of the day, if you do the math, we have 4 bit per symbol. And in the real plus now, the imaginary part, and that's a phase shift. So we shift the phase by 90 degrees. And so that's how you get the, this matrix. A little bit of a real-world example, and some of you might know this. This is an optical rotary encoder. It's going to be used in servo motors to find the position at the end of the day. And how does this work? So this slice disk is turning around with a certain frequency, and you have 2 detectors. And as I showed there, the lower one is the real part, and then a little bit physically moved with a little bit distance, there's the imaginary part. But now the important thing is we sample at the same time, always. And then just due to the fact that we sample at the same time and this disk is spinning around, we get a signal which looks like this, and it's phase shifted by 90 degrees. For sure, within a coherent transceiver, there are no spinning disks. It's done a little bit different, but that's actually how we enable a phase shift in the real world, just with that spinning slice disk there. So this was about the modulation itself. So we covered polarization, we got details about QAM, and now an important measurement is the signal-to-noise ratio, or OSNR called. What is it about? It's actually just the ratio between the actual signal plus the noise. And a good comparison is within that audience, you are on a really low noise level because you can hear me, hopefully, quite clearly and easily. And so we have a high OSNR ratio. If I would do the same talk in a cheering football stadium, I think it's going to be really hard to understand me, and the noise level is really high. So that's basically what also happens on optical networks. You really need to take care about a signal-to-noise ratio, otherwise the receiver is not able to detect it any longer, what's the actual signal is. And now coming back to our constellation diagram, which I introduced previously, how would OSNR look like on the constellation diagram? So we do have, on the left side, you see an SNR of 30 dB. And the dots are really easy to identify there, the 4x4 dots. Pretty easy for the receiver to detect. Now, going towards to the right side with an SNR of 20 dB, it's getting a little bit blurring already, but still possible to detect. But now looking at the SNR of 5 dB, this is like though it's not possible to detect any longer which bit belongs to which matrix section basically. And the receiver is not able to distinguish between 0 and 1s, so not possible. So it's a really low SNR here. Okay, so that's the theory part. Now let's move on. What we did last year, together with DKIX in Germany, they are running quite a lot of Nokia gear. We basically took a 400 gig coherent transceiver, plugged it into their gear, and looked how Nokia implemented it with the SROS. And we just run one command. It was the show port command, and I will go through it now step by step. What we see there, what is new basically compared to gray optics and traditional transceivers. So at the show port, these are basically 3 sections, and the first one is mainly characteristics of the transceiver itself. It's a fully tunable 400 gig coherent transceiver, and you see also the start and the stop frequency. Here it's shown in megahertz. Typically we use terahertz because the numbers are a little bit smaller, or channels. So this is 191.3 terahertz up to, and it's tunable up to 196.1 terahertz, or easier, channel 13 up to channel 61. The tunable is currently tuned to channel 23, and it does support a couple of grids, the well-known 50 gigahertz and 100 gigahertz for sure. Moving on, yes, we still have not DWDM, that's what we have, but we also have diagnostic monitoring. It should be known by now from quite a lot of you guys, and hopefully you have implemented in your network management system to monitor the diagnostic values. And I want to point out, typically TX and RX is for sure, we know the power levels, but I want to point out the temperature. In the optical industry, we are actually more heat generator than optical industry. So the whole power you feed into a transceiver, which here is roughly 17 watts, is mainly converted to heat. So let's say it's 16.999 watts what we generate on heat, and only a really small portion on light is coming out. So the actual light level of 0.001 watt, which is 1 milliwatt, or if you do the calc, you get 0 dBm. So that's our ratio. So actually we are not optical, we are a heat generator. And now bear in mind, if you have a 32 port switch with providing 17 watts on each port, this is more than 500 watts just for the optical components. We have seen vendors out there who say, okay, this is quite a lot of power. We first of all have to generate that power in our power supplies and feed it to the ports. We enable the high power mode. That's what they call it, a high power mode for the QSFP-DD port. But then we disable every second port. So your 32 port switch is at the end of the day a 16 high power port switch. So this can happen. So look in your data sheet and just ask your vendor, hey, do you support high power ports? Now coming to the coherent specific parameters, and Matthias already pointed it out, Juniper did some implementation there, and now we're looking at the Nokia's implementation. Arista did something there, and they're pretty much around the same. Yeah, I'll go through now step by step. So the first one is the RX channel. This is quite new. Before 10 gig DWDM traditional networks, tunables need to be tuned on the TX side. We still have to do this for coherent ones, but also we have now to set the RX channel that the local oscillator is locking on that frequency inside and knowing, okay, how to get rid of the carrier. There is no sweeping, so we can't detect the channel, so you need to know on which channel you're transmitting and receiving. Moving on there, dispersion was mentioned already. We have now two types of dispersion. So the first one is the chromatic dispersion. So what is chromatic dispersion? It is the change of the signal while it's traversing on the fiber, on its way actually from the transmitter to the receiver. And the longer your fiber is, the more your signal is be either extended, stretched, or pushed together. The DSP is quite powerful. It can compensate it. So it does it with some really fancy math to compensate the chromatic dispersion. And here you see in the positive way up to 2,000 picoseconds down to minus 25,000. But the more challenge is the positive one to compensate than the negative ones. And plus, you get a measurement device. So the chromatic dispersion is measured now actually in real time. So this is 220 picoseconds per nanometer. When you know the characteristic of your fiber, and we had here a G652.D, which has roughly 10 picoseconds per nanometer per kilometer, and you do the math, you might end up with 22 kilometers of fiber, which is not true. We ended up with 15 kilometers because we knew it's a 15 kilometer span, and we wondered, hey, where is those 70, 80 picoseconds per nanometer coming from, this offset? So we did a back-to-back test, just 2 meters of jumper cable, and ta-da, we had 80 picoseconds. We didn't know where it's coming from. There is an idea, maybe it's coming from the plugs, but we are not quite sure at the moment. So there is an offset. So the actual fiber was 15 kilometers. Beside chromatic dispersion, as we have now two polarization directions, we do have a polarization mode dispersion as well. And this is, here Nokia implemented it as different group delay. That's actually how both planes, so the Y plane and the X plane, are different with each other while they're traversing on the fiber. Here we measure 2 picoseconds, which is still in range, and the transceiver or the DSP, it can compensate up to 10, depending on what we are following, up to 20 picoseconds. It can compensate it without any issues. I mentioned issues, and issues are always measured for the bit error rate. So here you see the prefect bit error rate. Typically, we see it here, the prefect, which is entering before we go to the FEC. What is the FEC? It's the forward error correction. And this is also part of the DSP to correct errors, not only to detect, but we can also correct them. And this forward error correction is quite powerful, but it has limits. And the limits are shown as the RxQ margin. Nokia was quite creative there. We couldn't find the Q margin in the other industry around, in the optical transmission. Typically, it's called the Q factor. And what is the Q factor, the Q margin? How much gap is there still that the forward error correction is still able to correct errors? So if this margin is eating up to 0 dB, then the forward error correction is not, it still can correct errors, but on the post-FEC side, we will see more and more errors showing up. And then the upper layers, layer 2, layer 3, they will see this also in a bad transmission or a bad link. And it can turn out to a flapping link, for example. A back-to-back link had a margin of roughly 4 dB, so there was a lot of margin. And for sure, OSNR is also an important thing. Now on 2 polarizations again, we were running those 15 kilometers at 34 dB, pretty well, pretty good. We can go down to 26 or 24 dB of noise level, and if you go below, for sure, then your prefect error rate will go up again. So you need to take those values always in consideration and watch your prefect error rate precisely. That's an important outcome here. Just need to check where we are on time, because Matthias mentioned, we're good. Matthias mentioned a little bit about application modes at the beginning, and yes, that's pretty amazing. The Coherent modules, this is not only a just 400 gig module, it can also provide different application modes. Here you see 15 different, it's a little bit tiny, but it's the easiest one is like, let's say you can make 2 by 200 gig interfaces out of this Coherent, or a 4 by 100 gig, and even weird mixtures. That's pretty cool. What you see here now, I highlighted the Open ZR Plus OFEC. Actually, that's how we configured it, but the module was not capable to do it. So this was an OIF-based module. It's not capable to do the Open ZR Plus MSA or following it. So you need really to double check your data sheet. What is your Coherent module capable to do? And how you configure it in your switch, because there are different settings. And what is the difference there? I pointed out the optical parameters of OIF versus the Open ZR Plus MSA. So and yes, for sure, we have TX and RX levels. And on the Open ZR Plus, there is even more variation. They call it the 60L for low A version and the 60H for high power A version. And they typically differentiate there on the TX side, how high the power level is. But the interesting part is more on the, what I pointed out about dispersion and the OSNR tolerance. And there you really see that the CDR, chromatic dispersion tolerance for the Open ZR Plus is way higher compared with the OIF ones. And this also explains why you can, for example, use it, the Open ZR Plus, for more amplification, for example, longer distances, longer spans, and even the polarization mode dispersion is more tolerant here. Brings me almost to the end of the presentation. To summarize this, and I mentioned at the beginning, the DSP inside of a transceiver is now, in the small form factor, is, in my point of view, a game changer, because we can just, with raw and pure compute power, increase the bandwidth. And I'm pretty sure we will see this also for 800 gig or even beyond for 1.6 tera or even above. There are a lot of discussions ongoing, because the other method to increase bandwidth is to increase the frequency on the electrical side. And we are currently running at 50 gigabaud already, which is fast. 800 gig will move towards 100 gigabaud, which is even double the amount. It's really, really fast, because you still have to sample it. 100 gigabaud sampling is not that easy. You need special materials on the PCB as well. But with the power of the DSP, you even can quadruple or even 8 times make it way faster, which I showed here on this graph. This brings me to the end of the presentation. I'm really happy to take more challenges in terms of how did other vendors implement the coherent transceivers in their layer 2, layer 3 gear. So we did it with Nokia so far. We had a lot of fun at that workshop. It was really cool. And if you have gear and you want to see how the coherent modules are integrated in your gear and how it works, drop us a line. I'm really happy to take it. Thank you very much. And for sure, I'm still around for questions.
Thank you, Thomas. Any questions for Thomas? Well, you're here today and first thing tomorrow morning?
No, tomorrow afternoon.
Okay, okay.
Yeah.
Thank you very much again, Thomas.
Thank you.
Anna,